The third topic for this introduction is just to give you another more interactive exercise to think about Bayesian inference procedure, as well how to do it in the discrete case. So before we get there, let me just mention this again. So last time, I think I mentioned briefly, like the differences between frequentist and Bayesian, and in particular, in the frequentist point of view on the left, they consider the parameters fixed and the data is random. Okay? You have all of the properties of those tests that you can do because you think data are repeatable random sample. You assume that you can do this experiments for infinite number of times. And then they consider data as random and then parameters are fixed. So they always try to make inference about the fixed data. Whereas for Bayesian, here we are generically using theta as the parameter and y as the data. But anyway, so in the Bayesian framework, data are fixed. You have what you have. We don't make too much assumption about, well, what if I have a different sample and anything. This is what we have. But we always assume the parameter is random. Okay? So that's why earlier when we're talking about those two examples, we start with prior probability, collect data to the posterior probability, right? But then once we move to those parameters are random. We are not only talking about them in terms of probability, we talk in terms of distribution. Okay, so later you will see soon, even just today, that we're gonna have prior distribution for those data. We still collect data, and then we go to the posterior distribution of data. Okay, so earlier we've been talking about events, so we are talking about probability. Then when we talk about parameters in those models, then we are talking about using the languages of distribution. So we're gonna cover those in a minute. Yes. So for the Bayesian inference, generically you'll see that throughout this course, we're always gonna use the prior distribution as pi. Okay? And theta in this case is just a generic parameter in any model. So we use pi, theta, to denote the prior distribution. The sampling model, we're gonna cover how to do that. So this is how you think of data. Okay? And you can see we're thinking of data of y given theta. Okay? So y is your data, and theta is the parameter. Okay? So just give you a quick example, we're going to see that a lot in this course, is that a lot of times we assume that, like say, continuous measurements, we assume normal models for them, right? And in that case, we're thinking about y itself. They're following normal model. Okay? And then theta, if you think about parameters in a normal distribution, we have mean, right? We have standard deviation. So as long as you know this two, you determine your normal distribution. So a typical thing, say when you have a sequence of measurements and you want to know about the mean of that normal distribution, then you will put, so theta, just as an example, will become mu, okay, in the normal case. Okay? And then what you do is I want to make inference about mu, which is the unknown mean of the normal model. What I do is I put a prior distribution for mu, which is pi mu. Okay. So that's my first step. Okay. And then my second step, we will talk about what those distributions will be, okay, when we get there. But just to get you a sense of how the procedure works, is that then we're going to have this sampling model, which again, because we're already talking about using measurements, so those will be normal models. Okay, so that's where those normal density curves, all of those complicated forms that you have probably seen before, are going to come into play. And then lastly, what we're trying to do is to try to come up with the posterior distribution of this unknown parameter. Okay, so we keep using pi. Okay, so if it is marginal of pi for something, then it's the prior distribution. If it's the conditional, especially you will see that it's going to be conditional on the data, then we use this as posterior. Okay, so you get your prior, you get your data, and combine these two, you get your posterior. Okay, and all of this is going to follow Bayes' rule. So here, what I wrote on the slide is the Bayes' rule in the continuous sense. Okay, so that's why the marginal here is being expressed through an integration. And down here, when you're doing discrete, you're just going to replace the integral with sum. Like what we did earlier with the tort example is discrete, and there's only two outcomes, right? So we just sum up two joints, and then that's how it works out. Okay. So generically, this is still Bayes' rule. Bayes' rule on the continuous case. So all of the methods that we're gonna cover in this course is based on this Bayes' rule. And the subtlety here, of course, is, well, for different models, you might give different prior distribution, right? We're gonna learn different distributions, how to use them most effectively. But remember on Tuesday, I mentioned that a big chunk of this course is about computation. And the reason why computation is important is, well, how am I supposed to come up with this margin of y? Okay? You can always write it out. Well, that's easy. You just write it out like what we did over here. But numerically, how to approximate that is really complicated. Okay? So we're going to learn different methods. Like I said on Tuesday, Monte Carlo approximation is one thing. And then later on, when models are more complicated, when you have multiple parameters in the model, you're going to do what we call Markov chain Monte Carlo, MCMC. So all of those is trying to help to get you a good approximation to this final posterior distribution. Okay. So when we started, like soon, for the first two topics, you will see that when certain models are being studied, you will see what we call like a conjugate prior, in a sense that if you start with a family of distribution of theta and then combine with the data, you're going to come to the same, like a different distribution, but from the same distribution family. So those will be the cases that you know exactly what those pi theta given y is. Okay? If you know what it is, you don't even need to do any numerical approximation. So if I tell you it's a normal, then I know everything, right? If I tell you it's a beta distribution, which is something we're going to learn soon, then you know something about it. But then a lot of times you won't get an analytical solution for this posterior, and that's where those computation comes into play. That they can help you approximate it, even though we don't know exactly what it is. Okay? All right, so just get the big picture now, and let's come to a example here. And this is going to be a little bit more interactive. I just loaded my R Studio and on the Baxter server, so we can try that. So let's focus on proportion. That's the easy one to start with. We have this unknown percentage of P. Okay? And let's say we want to know the percentage of all Baxter students stay up at least one night last academic year to get schoolwork done. Okay? We don't know about this. You can essentially, I guess, in theory, ask everybody and then get that P. But of course, we're not going to do that. What we're going to try to do this in the class is that we're going to come up with two things. So remember, for doing Bayesian inference, we want the prior and we want the data, right? So let's get the data first, because that's probably more intuitive. It's like a quick survey. So suppose, so here we have a little bit more than 20 students. I'm just going to randomly sample 10. And I will just ask whether they stay up at least one night last academic year or not. Okay, so this is my data part. So keep in mind, this is data. Maybe for now, I'll just do it. So it's 10. So let's just take first two rows with maybe Jonathan. So it's 10 of you. So let me just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So okay, 10 people. N is 10. And I want, just tell us the truth. Whether you did it or not, just raise your hand for the first two rows and Jonathan. If you did, just raise your hand. 1, 2, 3. Okay, good. Thank you. So notice I'm recording the data in this way. We'll see why. Because at the end of the day, remember we need prior. So in this case, prior for P. And we also need the data model. Okay. Yeah, so for this kind of proportion, in a minute, you're going to see that we're going to use the binomial data model, because we're taking a sample and then counting how many people say yes. Okay, so a typical model is binomial, and we're going to cover that. And then the goal is to get the inference from the prior and data to the posterior. Okay, so my data is n is 10, and out of 10, I have 3 say yes. Okay. All right, so that's the data part. How can we come up with the prior? What we're going to do in the class is that, so first of all, we have to make the incorrect assumption that the 10 person that we just sampled is representative of Vassar. So let's just make that assumption for now. And the prior part, we're just going to build a simplified prior distribution. And what I'm going to do is trying to ask everybody in the class right now, and remote students, you can join as well, just to have a fun guess about Vassar students' behavior. And so I'm taking a discrete prior in this case. Okay, so P is the proportion percentage, right? So it can be anything between 0 and 1. Okay, for now, let's just say we have 11 possible values, so it's discrete. Discrete in the sense that I can only take finite number of cases. Okay, so 0, 0.1, 0.2, until 1, so it's 11 with increment 10%. So this is just the numbers that, or the values that this random variable can take, right? In order to come up with a prior distribution, we not only need to know those numbers, but we also need to know the associated probability to them. Okay, so that's what I'm asking you all to help come up with this prior distribution. So what we do is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 21 here, and remote students, do you want to join?
Sure.
Yeah.
Both of you?
Yeah.
Yeah, I'll pop my video open.
Yeah. Okay, so 20. Okay, so it's 23 in total. So in order to come up with a equal distribution, we have to only ask everyone to choose one number. And in the end, they all add up to 1. Okay, so we need a prior distribution, a proper distribution. So you have 11 choices. What I ask you to do, everyone, just to like raise your hand when I'm saying like say 0, raise your hand. Just make one decision, and then we're going to come up with the distribution, right? So we're going to count how many choose which, and then divide it by 23. That's the total number of people doing this quick construction of prior. All right, so remote students, you can just say yes when I count those numbers, okay? Yeah.
Sure.
Yeah.
So 0, anyone? Okay, we get 1. 0.1. 2. 0.2. 1, 2, 3, 7. Okay, 7. 0.3.
Yes.
Okay, 1 yes. 1, 2, 3, 4. 0.4. 0.5.
Yes.
Okay, 3. 0.6. 0.7. 0. 0.8. 0.9. 1, 0. No. All right, let's just double check. Yeah, so how many do we have here?
23.
23, right? Okay, awesome. So I just need someone to help really quick, just write down those numbers, because I have to like move to the computer, so really quick. So it's just 1, 1, 7, 7, 3, 3, 1, because the rest is 0. All right, so what we'll do is, it's on Uno, so if you want to put out that pre-written function and then try it yourself, feel free to do that. And what I'm going to do is it's a pre-written function, and we're just going to use the data. So the data is what? Y equals to 3 out of 10, right? And then the prior that we come up with here, they're just counts. But what I will do is in the setup, I will just have them divided by 23, so I have a proper distribution. So I'm going to just think really quickly what I should be doing. Okay. All right, so don't worry, I'm sharing it in a minute, so it will disappear. Okay, all right. So it's in our Markdown. So if you don't know much about it, don't worry. I will just show you how we can do this. So yeah, so as you can see, this is last year's data. It didn't change much. We sampled 10 people and then 7 said yes. In this case, it's 3, so I'm just going to update that. Last year, it was 19 people. So we have 23 this time. So I'm just going to do the tedious update here really quick. And you can sort of see the prior distribution from last year. All right. Okay. Anybody can tell me the list of the values that we have?
117733.
It's too fast. Give me a second. Okay, so 1
7 7.
So 1 1. Oh, okay. 1 1. Thank you. 7 7
3
3 3, and then all 0, right?
1
That one's 1. Yeah.
And then all 0. Okay, perfect. Thank you. All right. Okay, they're all zeros. Okay. Yeah, so you can spend time to read this function a little bit more carefully later. But pretty much you can see that I'm trying to set up the prior values. So remember, in order to get the prior distribution, you need to have the prior values and then the associated probability, right? So in R, we're going to specify the 11 values that I gave you to choose from. So it's 0 to 1 with increment 0.1. And the prior probability is the one that we came up with. And then this is the data. So we have all of this. You can run them here. Okay. And then here, it's a list of lines of doing all of the posterior computation. In a nutshell, what this is doing is that we're assuming that the data comes from a binomial distribution. Okay, so the point, like the part that we have to evaluate the y given p part, is going to be binomial evaluation. Okay, so if you know a little bit about R, you will see that we are using d binorm. That's evaluating the density of the binomial distribution. Okay, so we compute the data or like the sampling model from that, and then we just apply Bayes rule. Okay, multiply the prior with the data and then divide it by the total. Yeah.
Can you just increase the window size?
Oh yes. How can I do that? Okay, let me see. Does this work better?
Yeah.
Okay, thank you. Yeah. All right. So the data, like the prior, and then the data is here, and then this part is mostly. Okay, I think that's the best I can do. Yeah. So all of this is you can read it later. Don't worry about it now. We are computing. So this is the part about the data, the probability there, and then this is the prior times the data. Okay, and then you get each of the joints. Okay, by Bayes rule, you know that we need to get the sum of the joint, so you get the marginal in the denominator, right? And then you get the prior from there. So that's the gist of what this file, this set of lines is doing. So we're just gonna run it. Okay, and what I will do is I'm just gonna share with you what it would look like when we run all of this. So first of all, you can have a list, a data frame in this case, that will list the values of P, okay? The prior values that we came up with. So this is once we do those counts divided by 23, okay? And the posterior column here is just once we combine the data with the prior, what will be the probability for each of the p-value that we came up with. Okay? So not surprisingly, this come up as the top number, right? Because what the data tells us, the data is 3 out of 10, right? So p hat is 30%. Okay, and so there will be detail like behind the scene of how those posterior, how that is being calculated. But nevertheless, you will see that the posterior is indeed a combination of the prior and the data. Okay, and in the end, you can also plot them together. And it's not the nicest, I guess, just to use this. Well, I'm using the same color, but then with a different symbol for the prior and the posterior. So the circle is prior, and the triangle is the posterior. Okay, so this is the case, I think, is the 0.3 for P. Okay, so the prior, just between, I guess, 0.3 and 0.2, the prior was the same. Okay, Whereas now the data is driving that up because the data, the p hat or the data itself is telling us it's about 30% in this case. Okay. So I encourage you to try this out later. Actually, in fact, I think I did assign a homework question on this, so you're gonna have to deal with it a little bit later. But all of this, in fact, I try to use ggplot, all of the plotting schemes in those examples as well. So that's also part of our introduction to tidyverse that you're going to take on DataCamp. So you can come up with other choices. Say, for example, here, I'm just using different shapes. So I can show up prior and posterior as different shapes, the same color. If you change that, by the way, they accommodate British spelling and American spelling. And what you would do is you can, I think I just found here. Yeah, so there are all kinds of ways you can do it, and people have different preferences, and we don't care. So just choose the one that you like. And this is just some sample code that I'm sure will be helpful when you're trying to complete that homework question. Okay. All right, but anyway, this is just a quick demo of what you can do for a simple case as what we're doing in class. And then, of course, there is some stuff that I didn't get to talk about. Like I mentioned about the prior distribution. In this case, it's not a particular known distribution. We came up together as a class, right? But there are other choices that we can come up with. So that will be the core of the second unit that we're going to talk about. And also, when I talk about the data, like the probability of those, like d by norm, all of that, I mentioned it's going to be a binomial distribution, right? But then how exactly that can work out, et cetera, is going to be what we're going to cover after introduction for the first unit. Okay. Any questions? Okay. All right. If not, I'm gonna stop share here. Try to make sure that I get everything. All right, so you can try that out later. And so just lastly, the analysis goals in general for Bayesian, it definitely goes beyond just updating the prior to the posterior. You can also do estimation of unknown quantities, in particular the parameters that are unknown, but you want to know about them with good statistical properties. You can also do prediction. So the prediction in Bayesian methods will be very straightforward as we go through it. Like say pretty much you just like use the posterior distribution or the draws of those samples, and then you just make the prediction based on the model that you use. Okay, so all will be done through simulation. And you can also do hypothesis testing. So Bayesian hypothesis testing, again, so hypothesis testing in the frequentist, so I promise this will probably be my last time talking about frequentist, but the typical procedure of doing that is you come up with a null, you come up with the alternative, right? And then you're doing the hypothesis in that way. What we do in Bayesian point of view, remember, we can directly come up with probability statement about hypothesis. Okay. So if I write this, like what we did before, this is the prior, right? But once you get data, you can have hypothesis given data. Okay. Because they are directly probability statement about the hypothesis themselves. So the testing of procedure, I would say the test of hypothesis will be straightforward because it's a probability. If the probability is high, you have higher confidence in this. If the probability is low, you have lower confidence, right? Whereas, yeah, in the frequentist point of view, the p-value, all that is the reverse interpretation, right? And then you have to think that through more carefully. And lastly, of course, using all of that, you will be able to make certain decisions. Okay? So throughout the course, we're going to cover different aspects of this in different kinds of model, different kinds of data. But at the end of the day, it always comes from the base rule. Okay, and then of course the prior, the posterior, all that we're going to learn throughout the semester.